for this first video in chapter 8, and this is sort of where we start the trend that probably will last pretty much for the rest of the academic year, not just for this semester but in the next. Basically each chapter we're going to sort of be introduced to different functional groups and how they what their reactivities properties are. Usually every time we get introduced to a new functional group, we often think about how we make that functional group and then how that functional group reacts to make other functional groups, and that's kind of the pattern. And I talk about making functional groups and making compounds a lot because as organic chemists, one of the things that we're interested in is to be able to synthesize whatever structure of molecules we might want to synthesize for whatever reason. Oftentimes it has a biomedical, medicinal type of purposes to it. And anyway, so the first such functional group, well, I guess that we covered in the last couple chapters was alkyl halides, but here we have alcohols. And of course, to an organic chemist, alcohol doesn't just mean that like a drinking alcohol, which is ethanol solution, aqueous solution of ethanol, but anything that has the alcohol functional group. So in this video, we're going to talk about the properties of alcohols real quick, and then we're going to start discussing these sections 2 through 4 are going to be how we prepare alcohol molecules. Okay, and so we're going to do the first bit of that, but first let's talk about the properties of alcohols. And of course the main thing that stands out is they're kind of like water in that they can hydrogen bond, right? And that's of course because these guys have both very polarized protons as well as lone pairs, right? And that's because these protons, because it's attached to a very electronegative atom, oxygen, the protons are fairly partially positively charged, and so there's gonna be some hydrogen bonding going on, right? And there's gonna be like a network of these happening. Okay, and that's unique feature of alcohol functional groups. And maybe I should say this is. And because of that, I think we talked about this in the last couple of chapters, but alcohol is said to be a protic molecule because it has these protons that are available for hydrogen bonding. And maybe to go beyond that, because of this strong hydrogen bonding, these protons actually hop around on these oxygens. If you look at alcohol liquid, in this case we have isopropanol, right? These protons can be on this oxygen at a given moment, but because this hydrogen bonding is strong, this proton could hop over to this oxygen, and this hydrogen could hop over to this oxygen. So the proton-oxygen bond is not very permanent. It's always moving around, and that's another way of thinking about this as a protic molecule. Okay. It's because it's slightly acidic, and which reminds me, you notice like we're not covering the nomenclature of alcohols. That I think the best use of our time here, and even in the lecture video, is that maybe it's not the best use of time. So what I would have you do is every time we get introduced to a new functional group, please go study the nomenclature rules in the textbook. I don't think it's a good use of time for me to write out the same rules here in the video lecture videos. If you just read the nomenclature rules, I think it's straightforward enough for you to understand, and then we're going to be doing naming and drawing problems during class. So that's how we're going to roll. Okay, so the expectation is you're going to go read that section in the textbook, which I think is all outlined in the syllabus. So if you want to know which sections you're supposed to read up on for the nomenclature rules, please see the syllabus. Okay. With that, I think we mentioned that these protons are somewhat acidic, and that speaks to the this word amphoteric. Alcohols are amphoteric because they can act as an acid going in this direction, meaning losing this proton, or as a base. It's an amphoteric compound. It's both a very weak acid and a base, and that's what the word amphoteric means. And so when it's neutral, of course, that's what alcohol looks like. But because it's a weak acid, if it loses proton, it becomes a fairly strong base. Okay, and because it's a very weak base, if it gains a proton in this direction now, then it becomes a strong acid. In fact, the pKa is going to be around -2. The normal alcohol is 16. It's about the same as pKa of water. And then, of course, the alkoxide wouldn't have pKa because it doesn't have any proton. So this is called alkoxide ion. Anytime alcohol loses a proton, and notice that spelling with a K, and then of course this is alcohol, and I don't know if you know what this is called, but this is alkyloxonium ion. Remember from Gen Chem that like anions end with either IDE, ide ion, or ate ion, whereas cations always names end with em ion, like sodium ion. Okay. Now, we've also seen that alcohols are weak nucleophiles, and of course that was covered in the last chapter. Right, especially in the context of SN1 reaction. So I'll refer you to that. Now, to start talking about how we might prepare alcohols, one of those reactions, as we just mentioned, is an SN1 reaction, right? Like especially if you have a really good leaving group. And remember, this is a very good leaving group called tolsilite, which is short for toluene sulfonate. Remember, this functional group is a sulfonate group. It makes for a really great leaving group. Often this is abbreviated as OTS. Okay, this squiggly line just means it's attached to something, right? It's a great leaving group. Other examples included things like the iodo group and such. Hopefully you remember that from the previous chapters. So when you have really good leaving groups, and if you have a protic solvent like water, solvolysis or SN1 reaction, remember, is possible via the carbocation intermediate. And then this could end up with racemic if the mechanism is SN1, right? And remember that racemic means you have one-to-one mixture of these enantiomers. And that is because once the carbon becomes a carbocation, this is sp2 and flat, and so the water can attack from either side of that carbocation, so you end up with a racemic alcohol product. Now, if SN2 is the way we make the alcohol, where hydroxide has to be the nucleophile to make an alcohol, right? SN2 type reaction. Of course, the best scenario for that is when you have a primary leaving group, like primary iodide or primary tosylate or something like that. Right? Primary just means the carbon with the leaving group is only attached to one other carbon. Then you can easily make an alcohol via SN2 reaction. These are good for primary alcohols, right? Whereas SN1 was really best for not secondary but like tertiary alcohols, right? Because the tertiary carbocation is more stable. And why is that? Well, that's because if you think about the inductive effect, right, the carbocation is stabilized by 3 other electron-rich carbons, whereas secondary carbocation is only stabilized by 2 carbons and a hydrogen. Now, hydrogen hardly has any electron density at all, so tertiary is best for SN1. Now, SN2, the secondary is not as great, right? It can happen like so, but and then if it does, it experiences an inversion. But remember from last chapter that this could compete also with E2 product. Right. So it's not a really great clean reaction to make secondary alcohol. And of course, SN2 would never work for tertiary. So that's really just a review of the last chapter. And then in the next video, we're going to get into sort of new types of reactions to make alcohol. So see you then.